Okay, so armed with an understanding of what an integral is and the technical ability to compute them without doing a million different calculations, it's time to get to the real objective of this video, which is to be able to apply LRAM, MRAM, and RRAM into real-world situations. Let's start with a simple example, distance traveled. Let's suppose a particle starts at x equals 0 and moves along the x-axis. If you like to think about this as an ant, I do. Imagine the ant moving back and forth. It's traveling with the velocity of v of t equals t cubed minus 3t. And the question is, where is the particle at time 3? Now, looking at this question, I imagine you might just draw a blank for a second. Where is the particle? Well, I don't know. Step back and think about what the information given means. When the problem gives us v of t as a function, it's telling us the velocity function. When it says where is it, the particle, it's asking us to find the position. In other words, we're given a derivative function and we're asked to find the distance where it is at 3. In other words, the original total amount traveled from starting at 0. So this is an ideal situation to use an integral. We're given a derivative function, we're asked to find a total. If you don't yet see that this is a total, you'll get better at it with practice. One way to think about it is the position at 3 is the net amount of the distance. In other words, if the ant starts moving this way and then it turns around, and let's say it ends up right here at 3, the total amount traveled forward minus the total amount traveled backwards up until 3 tells us exactly where the ant ends up. This is not the graph of the function in question. This is just an idea I'm trying to give you to explain why the position represents a total here, because total is the key idea for integral. So we don't know how to take integrals yet, but we do get it that basically when we're looking for a total, we can just take the area under a curve. So we're going to want to sketch this function and then use rectangles to approximate its area. And when we do that, we'll have an estimate of the position of the ant. Let's get started with the sketch. Go ahead and graph this function. As we can expect, it's a cubic function. And we're looking for the area under the curve. Now, you do need to be a little careful because some of this area is going to be negative, and that's because in this time, the ant must have been moving backwards. Its velocity was negative. That's okay though, we can still use an approximation. Let's choose n equals 5, which means the width of each rectangle is going to be 0.6. And as you get better and better at these approximations, you actually don't need to draw your rectangles perfectly. You do need to know the endpoints of each interval. So I'm going to go ahead and just mark those out. I want a total of 5 intervals. The first one obviously starts at 0, and that rectangle will continue up to 0.6. If I add another 0.6, the next interval goes from 0.6 to 1.2. And the next interval is going to go from 1.2 to 1.8, and then 2.4, and then 3. And my rectangles aren't really drawn. What's really important is just the intervals, because now I can use this to set up an approximation. Let's go ahead and do both LRAM and RRAM, and then we'll take the average of the two as our approximate area. Pause here so you can compute it. When you're done computing it, use your calculator. What do you get for LRAM and RRAM? Awesome, so both of them obviously start with 0.6 times a certain height 5 times. With LRAM, those 5 heights come from plugging in 0, 0.6, 1.2, 1.8, and 2.4, because those are all the left side edges of each of these intervals. Whereas RRAM comes from 0.6, 1.2, 1.8, 2.4, and 3, which is all of the right side edges of each of these intervals. When we actually evaluate this, we get a left-hand approximation of 216 and a right-hand approximation of 1296. Now, those are really different numbers. For the purposes of this example, we can average them together. 1296 plus 216 is 15.12, and then divided by 2, we would get an approximate area of 7.56. But that's pretty unsatisfying. If you wanted to get a better approximation, what could you try? Exactly, you could try a higher n value. And I'm going to let you do that on your own time using technology. You can use the app or use your calculator. But fundamentally, you get the idea. Increasing n would increase the accuracy of our approximation. One final note, it should make sense that the right-hand approximation is a lot more. Because if you think about the last rectangle right here, the left-hand side is going to take a pretty low x value. And the right-hand side, when you cube 3, you go all the way up to 27, you end up a really large number on the right-hand side. So the difference in these two areas really mostly comes from the last rectangle. You can try visualizing that using the app if you want to try. Okay, fundamentally though, what does this number mean? Well, think about the units here. The total area here, the units for velocity are going to be meters per second or something like that if they tell us. They don't tell us the units, so let's assume that it's inches per second. So an area is going to be inches per second, which is the units for the height, times the units on the bottom, which is just seconds. Notice how these two units cancel out, and we end up with a total number of inches. That should make sense. A position should be measured in inches. Great. Let's try one last example and then we'll be done for tonight. The last example we have to talk about needs a little warm up here. I want to talk about cardiac output. So cardiac output is the amount of blood that your heart can pump. Healthy people should be able to pump 5 or 6 liters per minute, kind of at rest. But when you're exercising, it can go way up and your heart starts pumping a lot more blood so that you can get enough energy to exercise. It's important for heart patients, people who are at risk for having heart attacks or who have high or low blood pressure, to be able to measure how much blood their heart is pumping. And so one technique a cardiologist would do to measure that would be to inject some dye into this person's heart. And it's not a poison or anything, it's a harmless dye, but allows you, using technology, to then kind of get an image of how much blood is being pumped by your heart. And the way the image works is the imaging technology can measure the concentration of the dye after you inject it. So initially all of the dye is in the heart, and then little by little, as time passes, more and more of that dye slips out into the person's blood, and it disperses through the bloodstream, which allows us to see second by second how much of what was in the heart is getting pumped out, and that's what we want to measure. So this last example, aside from the interesting kind of medical connection, is going to show you that we can use this same method of rectangular approximation when we're given a data table. Instead of having a function and its equation, what we have is we have a bunch of x values, and then we have a measurement of a rate. In this case, the rate is milligrams per liter. We can calculate, if we imagine this being kind of like a curve that represents that rate, we can calculate the area under that curve using intervals defined by these points. So the first interval, for example, would be from 5 to 7, and the rate goes from 0 to 3.8. We could calculate the area from 5 seconds to 7 seconds. How would we do that? What would we multiply together? Right, so fundamentally we want to think about these first 2 points as if they create a rectangle. The first column is the x column, so the width of that rectangle is the distance from 5 to 7, which is really 2. And I'm going to keep writing the units just for this moment so that we can understand what we're doing. So we're multiplying 2 seconds times, and then we want some sort of height for that rectangle because we're trying to understand what it means to have an area under the curve. Well, the height would be one of these 2 values. It would be the first value if we want to do LRAM, because this is to the left. And it would be 3.8 if we want to do RRAM, because 7 is the point on the right. Now, usually the midpoint approximation is probably the best one to go to. So I'm going to calculate a number halfway between 0 and 3.8. And I'm just going to do that by adding these 2 together, 0 plus 3.8, and dividing by 2. and I get a height of 3.8 divided by 2, which is 1.9. Again, I just found the number in between the two y values. Now, I'm going to multiply that here, keeping the units, which are milligrams per liter, and I end up with kind of a weird number, but whatever that means, it does somehow convey the area of this little rectangle, a sliver of this changing quantity between these 2 seconds. So let's repeat this process for each of the other intervals. It would look something like this. And then when we take all of these areas of each of these rectangles, we add them all up, and we get a total quantity. And this number 55.17, which is the sum of all these rectangles, somehow represents the area under this curve. And now our job is to somehow use that total amount to answer the question that's actually given to us. And the trick is going to be to follow the units. So our current units are seconds times milligram per liter being the rate of change of the concentration. Now, what we want is an answer that is liters per minute. If you remember, cardiac output is a liter per minute. And we want to know how many liters, in which case we need to get rid of the milligrams unit. So I'm going to do something a little sneaky, which you actually won't have to do most of the time you do an integral problem. But I'm going to take this number, and I'm going to start with 5.6, and I'm going to divide it by the number that we just got. And the reason I'm dividing it is because I'm trying to cancel out the milligrams. Watch what happens. When I take the amount of dye we started with, and I divide it by the total area under the curve we just described, I end up canceling out milligrams on the top and the bottom. And I end up with 5.6 divided by 55.17, which is 0.101. And the units, since seconds per liter are on the bottom of this fraction, if you think about keep, change, flip, the units are now liters per second. And that's super close to what we want for cardiac output. We'd really rather have it in minutes. So if I just multiply this times the conversion factor, 60 seconds per minute, I end up with 6.09 liters per minute. And that's the cardiac output. You can think of it as the total amount that this heart has pumped through. So what do you need to know here? This last conversion is just because this is a real world example and there were some units problems. Basically what you need to know is if you start with a table, you can compute the rectangular approximations exactly as you would expect. You multiply the distance between the two x values times either the first y value or the second y value or the midpoint of the two y values for that interval. That's the last topic for today. You should be comfortable at this point using the left-hand midpoint and right-hand approximations and thinking about how area under a curve is present in real-world situations. Have a good night.